everyone, welcome to our talk, Hack Different, Pwning iOS 14 with Generation Z bugs. This talk is brought to you by Zhou Zhi and Xie JunDong. This is the agenda. The talk is mainly about 2 bugs used on 10 for Cup 2020 on iPhone category. This is the very first successful public challenge after POC has been introduced. We will cover materials from the attack surface to the bug and detailed steps of exploitation. Now, meet this new old attack surface. My previous presentation on Black Hat Europe 2020 talked about several effective cases that leverage inter-process JavaScript injection to escape Safari Sandbox on macOS. It's possible to directly bypass the sandbox without initial code execution just by abusing URL scheme. URL scheme is a vector for web to app navigation. Safari has a trusted list that don't require user action to automatically open an app, including App Store, mail, and digital contents from iTunes, and this applies to iOS too. What we were targeting is this com.apple.mobile store. It was actually not the first time that this pre-installed app got abused. On mobile Pwning 2014, Loki used this ITMSS URL to directly open a third-party website in iOS app where no sandbox was applied. It was assigned with CVE 2014 AA40. Since that, a trust list was applied. Before the navigation, iTunes Store downloads a list of trusted domains from this sandbox.itunes.apple.com and reads out the trusted domains list and compares the URL with that. Besides, it only accepts HTTPS and has SSL pinning, but Loki lately found a cross-site scripting on widgets.itunes.apple.com to pawn it again. Now, let's meet the first bug. Generation Z is used to describe kids born between mid to late 1990s and early 2010s. The bugs were both introduced before 2012, so they happen to be part of it. This first bug could affect a wide range of iOS versions, and it's easy to exploit. So part of the proof of concept is redacted to help protect users that stay below iOS 14.3 due to hardware limitations or at their will. Let's go back to iTunes Store. By auditing the following methods, we found another bypass. This is an URL first supported by iOS 3. The difference is that it still requires the domain to be trusted, but the URL of the page is not limited to HTTPS, making it vulnerable to man-in-the-middle attack. This URL is simply ITMS / and some part of it is redacted. Then we append a parameter named URL. It will navigate to the URL when the domain matches the trusted list. What surprised me is that it accepts data URL as well, where arbitrary HTML could be injected. So we don't have to follow the trusted list at all. In other words, this is a client-side reflected cross-site scripting. The limitation here is that it always appends a question mark at the end of the data URL, trying to set extra parameters. This breaks the base 64 encoding. So we have to use text plain here. This is the proof that the bug has been there since the year 2009. It's not a WebKit exploit, but WebKit attack. By using a simple location assignment, we escalate JavaScript execution to a special local WebView. And here's an alternative trigger named ITMS UI. It suffers the exact same bug, but instead it links to StoreKit UI services.app, which is also responsible for installing enterprise OTA apps. It has no navigation animation, so it's very low profile, but ITMS UI is not in the trusted list of mobile Safari, so it requires one more confirmation. But it makes no difference for other one-click vectors like AirDrop, iMessage, and third-party instant messengers that don't warrant for external app navigation. This bug was assigned to CVE 2021-748. So what's the difference for this WebView? First, this app iTunes Store is signed with dynamical signing entitlement. That means that it can use JIT. And this SU WebView is actually a subclass of UI WebView, where it uses in-process JS context bridge and in-process rendering. So this is a very special WebView that all of the WebKit exploit work here, both DOM and JIT. Some of the WebKit mitigations are gone. Since it's an UI WebView, there's no renderer sandbox. The only sandbox is the app container. So it's capable of loading shellcode in app context. But here's one thing, that it has no renderer auto restart. So the exploit only has one chance to run, otherwise this app crashes. So here we have to learn one thing named web scripting. With web scripting, JavaScript can invoke native Objective-C methods. Some of the data types are automatically converted between them. This is the bridge between two languages. JS context bridge is only available for the deprecated UI WebView. The actual implementation is in process within the renderer. In other words, the app itself. And in SU WebView, all of the methods are under this iTunes namespace of global disk. The methods are bounded to an instance of an SU script interface. There is a bridge named iTunes.telephony that exposes the current phone number and the operator name to the JS. It has a custom XML HTTP request implementation with no same origin policy. It limits the domains of the request but doesn't check for the scheme. So it doesn't matter, the domain name doesn't matter in the file URL, so this special XML HTTP request can be abused to read local files, but unfortunately it only supports string, and this app is Sandbox after all, so we cannot just simply read the photos at this moment. Since this app is part of the iTunes Store, Apple ID is visible to the JavaScript. It even has a utility to read the cookie from apple.com. I've noticed an interesting phenomenon that any outgoing HTTP requests will send extra headers related to the account, no matter what the domain is. For example, in this request, we can even see those critical tokens for two-factor authentication. With one more authorization header, it's possible to talk to the App Store server. And here comes the most interesting part. You can even get a list of all of the in-store apps and launch them by bundle identifier, for example, calculator. So this could have been the most embarrassing bug ever. It's only one cross-site scripting away from launching the calculator from web on the state-of-the-art phone, with no memory corruption at all. Now, it's time for memory corruption. First, it's a type confusion that don't crash, but leak useful information to us. This iTunes window has its setter and getter methods exported to JS context. We can assign an arbitrary Objective-C object with an invalid type to iTunes window. When we try to read the value, it always tries to invoke this tag method on the object we just assigned. So if you have iOS background, you must be very familiar to this message. When an unknown selector is sent to an object, the runtime throws a message like this with the address of the object. The funny thing is that we can catch this exception message in JavaScript, giving us the primitive for leaking arbitrary object. First, we call the setter to associate an arbitrary object, then use this iTunes window to trigger the selector. If the object doesn't have a method named tag, we can capture the address of it in this exception message. With this primitive, we break the ASLR without a further read primitive. Objective-C runtime uses various techniques to save memory, such as tag pointer and share instances. The address of certain data are always static from DSC. For instance, infinity in JavaScript maps to KCF number positive infinity. Simply by reading the address of Boolean false, we get the base address of every single library. Now this is a UAF with only 2 instructions introduced by iOS 6. In this method, if selector excluded from web script, it always returns 0. So what could possibly go wrong with this? Here's part of the documentation. It's too long, didn't read. Let's check out this highlighted sentence. You should expose only methods that you know are secure. To export a method, this function should return no for that method selector. So this is the access control between Objective-C and JavaScript world. By returning no, all of the selectors are exposed to JS, including this dmalloc, the free in Objective-C. This is also the root cause of our previous information leak bug that allows calling both the setter and the getter of a private property. Now it's literally free, then use. It should crash a message sent immediately with an invalid object pointer, showing that it's a use after free. By the way, this is what it looked like on iOS 6 when it was first introduced. This was assigned by CVE 2021-1864. Now, let's focus on the exploitation. Modern smartphones have evolved to make exploits harder. At this point, ASLR has already been bypassed, but we still got some million-dollar protections to take into account. This is not a traditional WebKit exploit, as some mitigations like GJCage, package, and structured ID randomization don't matter because we don't use WebKit for primitive at all. APR could stop us from easily getting shell code executed, but it looked promising to bypass. Pack is the major problem. And besides, the Objective-C runtime was hardened before the competition, which is our main concern. Now we managed to perform message send on control memory. The key to forge various classes for exploitation is the isa pointer, which tells both the type and runtime members of an object. Between iOS 14 to iOS 14.4, isa pointer is signed but not checked, leaving us the last chance to do the work. Now let's debug this exploit on an up-to-date iOS device without any virtual machine or research device. We can import these private APIs to the debuggable app. Since the UI WebView uses in-process rendering, all of the exceptions are catchable within the debugger. So let's load these private frameworks and initialize an SU WebView controller to load the HTML. And don't forget to enable ARM64E to play with the pack. Now it's time to build a fake object primitive. Let's first allocate a new object and hold a dangling reference. There are dozens of make blah blah methods that allocate different types of object, and the size of these objects are known to us. We can free them and reclaim the memory to turn into a type confusion, but we need a malloc primitive that can both control the learns and the content. First, I tried this address of an arbitrary learns NS string. This doesn't work for reclaiming the free memory because an SCF string has 2 forms, and in this case, it uses non-inline form that holds a reference to a string in JSC's heap. So, since we cannot allocate an arbitrary learns string in Objective-C's heap, this doesn't work, and so does array buffer. After a bit of reverse engineering work, I found this method which is perfectly binary safe and with controllable lengths. When calling this add multi-part data with name and type, it checks the URL. When it's a data URL, it tries to decode the data payload and put it in the same heap of Objective-C runtime. So it's perfectly binary safe and learns control. So here's the idea of the exploitation steps. First, we allocate a SU script XML HTTP store request, and we use this Facebook iTunes.create Facebook request to do the malloc. Just remember that this SU script XML HTTPS store request, its size is 192, so we have to create a string to convert to data URL that matches the same size. Now call the dalloc to get a dangling pointer and reclaim the memory. When we try to access this W, it's going to hit this. It's going to crash at message send, where we see the memory are controlled. Before 8.12, getting Objective-C message sent on control memory is enough for PC control, so we can use root to abuse the dynamic code signing entitlement and load shellcode. And this should have been the most privileged context that allows shellcoding, since JSC has been dropped on iOS. But now, it's still possible to do the selector-oriented programming. Actually, this is much harder after iOS 14.5 because of signed ESA and NS invocation hardening. At this point, we can forge arbitrary Objective-C objects. So with the leaked address, we have all of the ESA. And this fake object must be smaller than SU script XML HTTP store request. So my choice is to fake an NS data and cause its toString to leak the memory content, because finally it will cause NS data description inside, which yields the hex dump of the memory. So it's perfectly binary safe memory dumper. The contents must be less than 24 bytes, or otherwise it will be truncated. But I can repeatedly use it to dump the whole memory range. The fake structure looks like this. First, the ESA is none, and the learns, and followed by the location is. So it's perfectly arbitrary read with arbitrary learns. Just and don't forget to keep this deallocated member to keep it as now. Otherwise, it's considered a function pointer and call and free this NS data laterally and call this function, which will obviously crash. Now we can use an even better fake object primitive, because currently this malloc primitive returns an immutable buffer. It's better to use an array buffer because it's mutable. We can modify the forged object on the fly and reuse them. And we need a much bigger buffer for various fake objects and post-exploitation. Here are two approaches. Number one, the heap spray approach. First, we need to heap spray plenty of array buffers. Now, when we're trying to refill the dangling pointer with a fake object, we use a fixed address to build an NS array where the content points to a fixed address. If it hits one of the array buffer, we try to dereference this pointer should result in a nested NS array. And in this array buffer, we fill them with thousands of different NS array where the number inside this array is the identifier. So now we read the description of this fake object. It's basically when it hits one of the array buffer, it will be treated like a nested NS array with one number inside. So by reading the description, we can know which array buffer hits the target address. Now trigger garbage collection to release the others and keep reusing this only one array buffer. In this approach, I use the tag pointer to build the fake NS number. On iOS 14, tag pointer has been hardened using an obfuscation. Before, it was clearly to see the bits and number, but after the obfuscation, it seems totally random. At this point, we can still use address of primitive for thousand times, but when it comes to heap spray, it's going to be very slow because it throws an exception every time and emits system logs. So what's inside this tag pointer obfuscation is that an Objective-C debug tag pointer obfuscator is randomized per process. The tag pointer uses XOR to obfuscate it. Since we have this address of primitive with one known pair of float 64 number in JS and the obfuscating pointer in Objective-C, it's possible to calculate the arbitrary value using the following algorithm. But after the 10th cup, I found another better approach without heap spray. Because, as I mentioned before, this app can only crash once. So, if it crashes, everything stops. So, heap spray is less reliable. We can use this arbitrary read and address of primitive to leak the backend store of an array buffer directly. At this context, the address of the array buffer is the data pointer is protected by package, but it only matters to WebKit since we don't have to build a fake int A array with fake vector pointer. It doesn't matter at all. All we gotta do is to strip the signed bits to get the real address of the backend store and use it to create various fake objects in Objective-C, as Objective-C don't check the pack for it. So let's get into the slop time. This is an exploitation technique invented by Project Zero. It uses a series of NS invocations in an NS array. It calls NS array make objects perform selector invoked to perform invocations respectively. So with proper gadgets, it's capable of calling arbitrary C functions. But after Project Zero published its iMessage zero-click exploitation, Apple added a 32-bit random cookie to NS invocation to prevent exploitation. Since we already have the ASLR bypass and arbitrary read, we can read this number from this magic cookie.o value to get this random cookie. And what's more, we need a Kickstarter to call the invoke method on deallocation. It must have been a dealloc method that performs invoke selector on a member of self. This is a candidate we found in this iTunes store that it calls invoke on offset offset and a certain offset to kickstart a slop chain. But we still need a double free primitive because we have to call it dealloc method. But this SK story view controller is not a subclass of SU script object. Just to remember, why we can call this dealloc is that the is selector excluded from web script returns 0, false. But this is not a subclass of SU script object. So it falls back to the default implementation of NX object, where it doesn't allow the alloc method. We cannot simply call this the-alloc in JS. My workaround is to find a class that is a subclass of SUScript object, and it has a setter for associating other SUScript object to its properties. It releases the external references to the objects upon the allocation. Here's our candidate, SUScript segmented control item. It can be allocated in JS by calling iTunes.make segmented control.create segment. And it has a property setter, set user info, that accepts arbitrary SUScript object. Now, the steps are like this. We allocate a new item as an object A. Now, allocate new object B to lately become a dangling pointer. Here we chose SUScript window. Now we assign the object B to the user info property before triggering the UAF. Now we can free object B and reclaim it with a fake NS array. So we use the array buffer to prepare for the slab chain to build everything we needed, the NS invocation and this targets, this cancel request, and this fake store review controller. Now we call this the-alloc on object A to free everything again and kickstart the execution. The fake code looks like this. On iOS 14.3, these signing gadgets were still available. We can use this signing gadget and call arbitrary seek functions using drsim and invoke using implementation. But here's a known limitation that Project Zero didn't solve that. When using those gadgets invoke using IMP, the first argument of the seek call, which is the self pointer, it cannot be 0. I solved this problem because I have to use this C function calls with the first argument as 0. So I solved this problem by using callbacks. For example, this cfSetApply function from Core Foundation fully controls up to 2 arbitrary arguments. First, I can build a fake set object. Now I call this setApply function with a assigned pointer on it. The second argument is the sign function pointer, and the third function argument is the context applied to this exit function, which is the second argument. And the first argument is the second member of this NS set. So, at this point, we need to load shellcode. We use this well-known perform JIT memcopy gadget to write the JIT region. This is actually pthread JIT write protect np and memcop inside. Some special registers needs to be altered to change permissions of the JIT page. It used to be inline everywhere, but don't know why this function is public on iOS 14. Which made the exploit extremely simple with our primitives. So Apple inlined this function again after 10th cup. So after loading the shellcode, I still need a pack bypass to jump to the shellcode. In theory, I can obtain a sign pointer to a JIT function first, then override its machine code. But I chose a more straightforward approach instead. That to find an unprotected global offset table pointers. These are unprotected jump to unauthenticated function pointers. Here's an example. In this Swift, in this function of Swift runtime, it loads a function pointer from a writable global offset table entry, and it calls this function inside, where the second argument is the function pointer with an indirect jump with no authentication. This is assigned by CVE 2021-17-96. I will first use dr-open to load this Swift runtime library and use arbitrary write primitive to override this got entry with the pointer to the shellcode. And finally, I call this function to jump to the shellcode. It was patched by Swift runtime after 10 for cup. Now, since we have the shellcode execution, it's easy to spoil all of these registers like this. For the post-exploitation, this app is pretty privileged that it can access contacts, camera, and SMS, and even Apple account settings, and install MDM profile to gain persist traffic monitoring. And don't forget that since we have shellcode here, we can load further jailbreak payload. It has much more IOKit and userland services compared to the WebKit JIT process. Here's the takeaways from this talk. We have present 2 bugs from late 2000s that still beat state-of-the-art mitigations. And sometimes you don't need a single byte of memory corruption to run a unselected seed calculator from web. Plus, get the victim's Apple ID and phone number. With decent tricks in order to bypass those $1 million protections, and some of the instant messengers can also be the effective vectors for the URL scheme bugs we talk about today. This talk has so many references to the following materials. If you want to go further on this topic, I strongly recommend you to read them. Thank you for listening to the talk today. If you have any questions, feel free to ask them. Thanks.